Hey guys, welcome back to chapter 5. In today's lecture video, we are going to look at some more difficult examples of Lewis structures and talk more about the double and triple bonds. All right, so in your textbook, in this chapter, they talk about something called diatomic molecules. So there's really no good way to slide diatomic molecules into this chapter. So I just kind of throw it in here at the beginning of this lecture, and then we'll look at some diatomic molecules. So hopefully that'll drive it home. Diatomic molecules are di is the prefix for two, atomic, atom. So diatomic molecules consist of two atoms. So these diatomic molecules will always exist as pairs of atoms. You'll never see them by themselves. There are 7 diatomic molecules that you guys just need to memorize, just know. I tried to think of a really cutesy example to help with remembering the 7, and it worked out great until it didn't. So there's 7 diatomic molecules. The diatomic molecules start on the element nitrogen, which coincidentally enough is the 7th element on the periodic table. So I was like, cool, this is going to be a really fun example. This is going to work out. So the first 3 diatomics are nitrogen, oxygen, fluorine. And then as we work our way down from fluorine, they kind of make the number 7 on the periodic table. So if you were to trace across these 3 and then down the halogens, it looks like the number 7. So this was working out great until it wasn't. So we've got nitrogen, oxygen, fluorine, chlorine, bromine, iodine. These are all diatomic molecules. But then we've got hydrogen, which kind of ruins all of this really cool example. So it almost worked out really great, but hydrogen ruined everything. But what you need to know is these are the 7 diatomic molecules, so you'll never find nitrogen just by itself. It will always be N2. You'll never find chlorine by itself. It'll always be Cl2. So again, something we introduce now, and then in the next module, or in the next unit, I should say, when we start doing chemical reactions, it'll be important that you know these diatomics. So I'll say something like oxygen reacts with hydrogen, and you automatically need to know that O2 reacts with H2. So that's what you need to know for diatomics. So since we introduced diatomics, let's go ahead and ride this wave and look at some more difficult examples of Lewis structures. So why do halogens form diatomics? So let's look at one of these halogens and look at how it forms a diatomic molecule. So the diatomic molecule that we're going to do the Lewis structure for is going to be Cl2. So we're going to do the Lewis structure for chlorine. So remember, going through our steps, the first step is to determine how many total valence electrons were brought to the party. So chlorine has 7 valence electrons. There's 2 atoms of chlorine. So that's a total of 14 valence electrons at the party. Okay. Step 2 is to draw the skeletal structure. Well, there's 2 chlorines, so not a lot of variation here. They're going to be right next to each other. So chlorine and chlorine. And then the third step is to distribute electrons, filling as many valence shells as possible. So again, I always start with a bonding pair. So 1, 2, and then I'm going to keep distributing until I get to 14. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. All right, so I've used all 14 valence electrons that were brought to the party. Now I need to just make sure everybody's happy. So again, we're striving for octets here. We want 8 valence electrons for each atom. So if I look at this chlorine on the left, I have 1, 2, 3, 4, 5, 6, 7, 8. So he's happy. And same thing for this chlorine on the right. So this is the Lewis structure for Cl2. I want you guys to try another diatomic molecule, okay? So I want you guys to try the diatomic molecule O2. So we know it's a diatomic. We know it exists as O2. See if you can draw the Lewis structure. So pause the video and go ahead and try. All right, so step one, what is the total number of valence electrons brought to the party? So oxygen has 6 valence electrons. There's 2 atoms of oxygen, so that's a total of 12 valence electrons at the party. Okay. Step 2, and then that leads us right into 3. So step 2 is to draw the skeletal structure. Again, there's 2 atoms of oxygen. Not a lot of variation here. They're going to be right next to each other. And then step 3 is to distribute electrons, filling as many octets as possible. So I always start with a bonding pair. Draw that a little bit better. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So I cannot put any more electrons onto the paper because I do not have any more electrons at my disposal. I had 12. I put 12 down. What's the problem with this? Well, if I look at this oxygen here, we're striving for an octet. How many electrons does he have? Well, he has 1, 2, 3, 4, 5, 6, 7, 8. So he's happy. He's good. But what about this guy over here on the right? He's got 1, 2, 3, 4, 5, 6. Well, that's not good. He is not happy with 6 electrons. He wants 8. I cannot just throw 2 more electrons onto the paper. I do not have any more electrons at my disposal. I don't have any more sodas in the cooler, right? They're just not there. So this is that case. This is the step 4. If and only if, so this is a last resort, if and only if we have an atom that lacks an octet, what we can do is create what we call a double bond or eventually a triple bond. So instead of these 2 oxygen atoms just sharing 2 electrons, I can take a lone pair from somebody that is already happy, and I can throw that lone pair into a bonding pair. Okay. So I just simply moved these 2 lone pairs and I made it a bonding pair. Now these 2 oxygens are sharing these 2 oxygens are sharing 4 electrons instead of just 2. So when we move electrons around, it's really, really easy to forget to erase them or add too many. So I always like to double check that there's still 12 electrons on the paper. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I still have 12 electrons on the paper, so that's good. Now we want to see if everybody's happy. So this guy on the left was happy. Let's see if he's still happy. He's got 1, 2, 3, 4, 5, 6, 7, 8. So he's still happy. And this guy on the right now has 1, 2, 3, 4, 5, 6, 7, 8. So he has gone from sad with 6 to happy with 8. So this right here is called a double bond. What a double bond is it's 2 atoms that are sharing 4 electrons. So here we see the process of moving those electrons. Here is depicting those electrons as dots instead of lines. And then here's where I depicted it with lines. So there's no rule that says we can only share 2 electrons. We could share 4. And then a triple bond would be an example of 2 atoms that share 6 electrons. So it looks something like that. Okay. So that's a double and a triple bond. Okay. All right. So the last little example that I want to talk about in the slideshow before I tell you guys to go off and practice is these polyatomic ions. Okay. So the first thing I'm going to do here, I want to draw the Lewis structure for this polyatomic ion. So the first thing I'm going to do is what I do for every other Lewis structure. I'm going to determine how many valence electrons are at the party. So hydrogen brings 1, carbon brings 4, each oxygen atom brings 6, and there's 2 of them. If I simply add all of this together, I've got 12, 13, 14, 15, 16, 17 valence electrons at the party. What is different about this number? Well, up until this point, every problem that we've practiced has had an even number of valence electrons at the party. And remember, we've always talked about electron pairs, bonding pair, lone pair. So the fact that this is an odd number should send up a red flag right away. We are not going to do Lewis structures with an odd number of valence electrons. They exist, we're not going to do them. So there must be something else that we're missing here. And there is. It's this guy right here, the charge on that polyatomic. How does an atom or a particle become charged? What was there that happened? Yeah, there was a transfer of an electron. So if this particle has a negative charge, that means it must have taken or stolen an electron from somebody else. Because it has that extra electron, we need to throw that into the cooler, throw that into the pot. So we need to make sure that we acknowledge the charges on these polyatomic ions and make sure that in this case, we add that 1 extra electron to the pot. Now, when I add this all together, I've got 18 valence electrons. We have an even number. We can start moving forward. Okay, so make sure you acknowledge these charges. So what I want you to do now is I want you to go ahead and pause the video and see if you can draw the Lewis structure for this. The other wrinkle here is that there's 3 different types of atoms. And I will tell you right now that carbon is the central atom. The hydrogens and oxygens are around the carbon. So go ahead and pause the video and see if you can get this Lewis structure. All right, so moving through our Lewis structure. Step 1, number of valence electrons. Step 2 is our skeletal structure. So as I said before, carbon is our central atom. And then we've got our hydrogens and oxygens around the carbon. Step 3 is to distribute electrons, filling as many octets as possible. I always start with bonding pairs. So 1, 2, 3, 4, 5, 6. Then I go around and distribute the rest of the electrons, filling as many octets as possible. So hydrogen's good, right? Remember, hydrogen wants a duet. So I'm not going to give him any lone pairs. But I've got 6 electrons on the paper, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So I've used all the valence electrons at my disposal. Is this the Lewis structure for this polyatomic ion? No, it's not. Who is not happy in this case? Yeah, carbon, right? So if I look at carbon here, he wants 8, and he's only got 1, 2, 3, 4, 5, 6. So the way that this Lewis structure is drawn, he is not happy. I don't have any more electrons to throw at carbon. I've used all the electrons that are at my disposal. So what can I explore to try to make carbon happy? Yep, we're going to do a double bond. In this case, it doesn't really matter what oxygen you pull from, but you're going to pull from oxygen because they're happy. So let's say I pull these 2 lone pairs and I throw it into a double bond. There we go. All right, so again, just need to double check that I still have 18 electrons on the paper. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So I still have only used my 18 electrons. Now I need to make sure that everybody's happy. So this oxygen up here, 2, 4, 6, 8, he's happy. Oxygen on the right, 2, 4, 6, 8, he's happy. And now look at carbon, 2, 4, 6, 8. He is now a happy guy. So this is the Lewis structure for this polyatomic ion. All right, now we can go back to this list of rules, and now we can address all of these helpful hints that I put into this list of steps. So step 1, calculate the total number of valence electrons. We need to make sure that we consider any charges on the ions. So if it's a negatively charged ion, we need to make sure that we add in 1 or 2 or 3 extra electrons. If it's a positively charged ion, we need to make sure that we subtract 1, right? A positively charged ion gave an electron away. So we need to subtract 1. Step 2, write the skeletal structure. So hydrogens will always be terminal. Try a symmetrical approach. And the other one I should probably add in here is if carbon is available, it will always be the central atom. So carbon will always be central. Step 3, distribute electrons, filling as many octets as possible. So up until this point, you've seen me do this step just one way. What I want to do now is I want to address this helpful hint at the bottom. So this is a helpful hint that your textbook offers. So it's something that I do at least want to address and show you how it works. And I'm actually going to use the previous example to walk through this. So this helpful hint says the following. We're going to take the number of electrons that would fill all the valence. So how many electrons would make everybody happy? For the most part, everybody's going to want 8. Again, the one exception is hydrogen. So we're going to calculate, well, what would make everybody happy? We're going to subtract that number from the number of available electrons. So we already do this. This is the number of electrons that was brought to the party or that's available at our disposal. So that's the number that we've been calculating. So the number to make everybody happy minus the number available, and that will tell us how many electrons are bonded. Okay, so how many electrons are in a bond. So let's go back to that example and see how this predicts things for us. Okay, so we've got the number to fill all valence minus number available equals number bonded. Okay. So first, the number to fill all valence. So how many electrons would make hydrogen happy? Remember, hydrogen's happy with a duet, so 2. How many electrons would make carbon happy? Carbon wants an octet, so 8. How many electrons would make Oxygen happy or fill oxygen, 8, and there's 2 oxygen. So when we add this together, we essentially have 8 times 3, which is 24, 25, and 26. So the number to fill all valence would be 26 electrons. We're going to subtract that. I'm going to switch colors here. We're going to subtract that from the number available. So that's, again, how many electrons does everybody bring to the party? So that's 1 from hydrogen, 4 from carbon, 6 from each oxygen, and then the charge gives us 1. So remember that we had 12, 13, 14, 15, 16, 17, 18 valence electrons at the party. So we're going to take 26 minus 18. 26 minus 18, and that's going to give us the number of electrons that are bonded. So let me go ahead and type that in, 26 minus 18, and that tells me that 8 electrons are in a bond. And remember, electrons bond in pairs. So very often students will say, or that tells me there's going to be 4 bonds in this structure. Okay? So 8 electrons that are in bonds, or since they bond in pairs, 4 bonds for this structure. Well, how is that helpful? What does that help us to predict? Well, if I do the skeletal structure for this compound, remember it looks something like this, I have predicted that there's going to be 4 bonds. So if there is 4 bonds, but only 3 atoms around the carbon, what does that predict about one of those bonds? Yeah, it must be a double bond, right? So 8 electrons in a bond, or 4 bonds, we're going to have 1, 2, 3, 4 bonds. So that's where this helpful hint is useful. It's going to help you to predict when there's a double or a triple bond, or predict when it's just all single bonds. Once you have this on the paper, then you can go ahead and fill in the other electrons. So I've got 8 electrons on the paper, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So again, we come to this same structure. So that helpful hint, it works great for some students. It absolutely blows other people's minds. So if it just blew your mind, don't use it. Use the other way. But some students find it really helpful, so I like to at least offer it. Okay, so that was step 3. And then step 4, if an atom lacks an octet, explore double and triple bonds. Again, I just want to throw out a word of caution here. This is an if and only if case. This is a last resort. And when you guys start to use double and triple bonds, use them one at a time. Y'all love some double bonds. So what I see often is I'll see a structure that looks like this. And you guys will be like, oh, carbon's not happy. Let me put some double bonds in here. Whoop, whoop, whoop. Okay, that's too many double bonds. Carbon is still not happy because he has way too many electrons. So when you guys are using these double bonds, use them sparingly as a last resort. So start with 1 double bond. See if that fixes things. If it doesn't, try another one. But these are last resort. Use them only if you need them. Okay. So that's it for Lewis dot structures. At this point, I would highly advise you to stop and practice. Don't move forward. Do some Lewis structures. Do some practice. Chem 101 actually offers a really, really great tool for this. So if you go to, I think it's settings, and you'll see free draw. It'll allow you to just kind of play with and practice Lewis structures, putting bonds in, putting lone pairs, and it helps you with adding everything up. So Chem 101 is a really great resource for this chapter. And then also just Googling Lewis structures. and you'll get more worksheets with the answer key than you have time to do. So that would be another really great resource to stop and practice at this point. So that's what I would do before you move forward. When you are ready to move forward, we're going to do three-dimensional structures. So we're going to take these two-dimensional dots and lines, and we're going to pull them up off the paper and make three-dimensional shapes, because that's how molecules exist in real life. So I hope you guys found this helpful. Happy practicing.